Today we're going to start Module 11, Lesson 10, which is entitled, Are the Units of Area Always Squared? And we're going to look at it and find that, nah, not really. So what do we have here? We have a graph that shows the estimated cost in dollars per foot of a building, the first half of the suspension bridge. The first 500 feet of the bridge is called the anchorage. That's this section right here. And then the support for this, which is the support for the suspension part of the bridge. For this portion of the bridge, the cost is the same per foot. However, as the construction moves further away from land, the cost becomes more expensive. And you can see that is taking place. The further you are from land, the more expensive the cost is. So your first task is to pause this video and answer the first 3 questions. Go ahead and do that now. So question number 1 wanted us to label the horizontal axis properly. Remember, the horizontal is like the horizon that we watch the sunset over. And labeling it properly, well, that is going to be distance from land. And we're going to take and measure that. The unit is going to end up being feet. Let's actually spell that out a little bit better there. So the distance from land is feet. So we've answered question A. Label the vertical axis properly, and what is its unit measure going to be? Well, this one, the vertical axis is going to be cost, and that is going to be in dollars. So we've labeled both our vertical axis and our horizontal axis. In question C, what is the meaning of 0.590,000? Well, 0.590,000 takes place right here, and let's change that to red so it'll be seen a little bit better right there. And the meaning of that point is that at 500 feet from the starting point, or from the land there, that's going to be $90,000 per foot of bridge. So that, really think about that. $90,000 for that much bridge. Wow. So we've answered part C, we will type it in right here, saying that in text that at 500 feet, the cost of, there we go, the cost of the bridge is $90,000 per foot. Now, they want us to take and connect these 4 points. So we're going to go ahead and do that, and when we do, it's going to create a rectangle. And the 4 points we're looking at, they gave us 0.00, which is right here, 0,500, 590,000, and 500, and by doing that, we have taken and created for ourselves this rectangle right here. So that is going to be the answer to part B, the start of the answer part B, and it says, what is the area of this rectangle? Well, we know the formula for the area of a rectangle is going to be length times width. And we can see that our rectangle is going to have a length of 500 and a width of 90,000. So that's our y value. Our y value is this distance right here, and although it is much smaller in distance than our 500 is, it represents a much greater number. But remember, that is dollars, where the other one is going to be feet. So I'm going to take and write this down as my length is going to be 500 feet, and my width is going to be $90,000. Now, this is a good opportunity for us to use our dimensional analysis. If we were to take it and multiply that out, oops, I left something off there. That's $90,000 per foot. So if I was to take and use our dimensional analysis here, we can take and set up a chart like we've done before, where I'm going to take and put some lines in here, here, and here. And what am I actually multiplying? I'm multiplying 500 feet times $90,000 per foot. Per means divided by. When we do that, our feet are going to end up dividing each other out here and here. And that means what unit is left? Only dollars. And then from there we could take and multiply our 90,000 times our 500. 500 times 90,000. And that's going to equal to, holy cow, $45 million just for that Anchorage portion. So we would say their final answer for that area is equal to $45 million. And don't forget to include your units. Now question number 5 seems hard, but it really isn't that hard, because it says if we could draw a geometric figure to cover the remaining portion of the bridge, so that's all the blue stuff there, if we could create a geometric figure to cover that, and could determine the area, what would the units be for the answer? Well, the units would be the same thing we have right there, which is dollars, being the total cost of creating the bridge. Let's turn the page. Number 6 says connect points, alright, to form a trapezoid. The height of the trapezoid is going to be your horizontal axis. So let's jump back over here and work on that. So I've got 500, 0, and then I have 590. So that's going to be 2 of my points. We can get a different color here. Let's do hot pink. So point 500, 0, and 590,000. And then I also have points 1,024, 240,000. So let's go back and do that. So at 1,240,000, you see that point's already labeled there. And the other point is going to be at 1,000. And we are going to connect those points with a line as well. And I guess I'll use neon green. Oh, that's not neon green. Let's try that again. I know what I did wrong. Right here, so that we can get our pink in there. So now we can take and connect those points just like that. And when we do, what did we create? We created a trapezoid. And it said that the height is going to be the distance between the parallel lines. So this distance right here, that is actually going to be the height of our trapezoid. And that would be, of course, 1,000 minus 500, which is going to equal to 500. Our basis of our trapezoid is going to be 0 to 240,000, so 240,000 is going to be one base, and 0 to 90,000, so 90,000 is going to be the other base. So jumping back over here and answering the questions, our height that we discovered is going to end up being 500 feet. The lengths of the basis, including your units, well, that we discovered was going to be $90,000 and $240,000, including our units. And then to find the area of a trapezoid, include units in your calculations. Well, we know that area is equal to 1/2 times the height times base 1 plus base 2. That's the formula we have for the area of a trapezoid. So area is equal to 1/2 times our height we discovered is going to be 500 times the sum of base 1 and base 2. That's going to be $90,000 and plus $240,000. And I realize that I made a mistake up here because both of these would be per foot and per foot. From here, we're going to keep working through it. 1/2 of 500, that's 250. That's going to be 250 plus, not plus, times the sum of 90,000 and 240,000. That's going to become 330,000 right there. And then from that, we're going to multiply, and we'll let you use your calculator on that. 250 times 330,000, and that's going to equal to the area of $82,500,000, and that is going to be just for that one small section of the bridge. So that one little bitty pink section of the bridge that we looked at right here, this section alone is going to be $82,500,000. Now, what do I want you to do next? I want you to take and create the next trapezoid. Work number 7 on your own and find out what the area of that is going to be, which is going to be the cost for building that portion of the bridge. How'd that end up working out for you? For me, when I drew it out, it ended up giving me this thing, which I did in the bright green, where I had a height. The distance between my parallel bases was 750. One of my bases is 1 million. The other base was 240,000 that was right here. I plug those values in, as you can see right here, to my formula, adding them together to get 1,240,000. Then I said half of 750 is 375, and I multiplied that times 1,240,000, and that gave me 465,000,000. Whoops. Hold on just a second. Gotta get my device working again here. 465 million, which is going to be the answer for that triangle. Now, I've decided that I was going to keep track of all those by writing them in where they represented. So you can see I've got my 45 million here, my 85,500,000 written here, and my 465 million written here. The next question wants us to take and find out what the area, total area on the bridge is. What if we were to add those up together? So we had, let's pick a nice pretty strong color now. So pick our blue. So we had our 45 million, which was our first section. After that, we had, what was it? 82,500,000 is our next section. So we're going to take and do 82,500,000. And then from there, we had the last section, which was 465 million. So I'm going to plug that in right here. 465 million. And we have to add all those values together. Give me a 0, a 0, a 0, a comma, a 0, a 0, a 5, a comma, a 12, and then I'm going to have, that's 12, 18, 19, and then a 5. So it's going to cost $592,500,000 is going to be what the area of the underneath that trapezoid is. Question is, what does it mean? That means that the first half of that bridge, the cost of building from this point all the way over to that peak point, which is the center, the halfway between the two shores, is going to be that colossal amount of, what was it, 592,500,000. And I took and typed that in right there. For part 10, it says, is the answer to question number 8 going to be an underestimate or an overestimate? Justify the answer by using the shape of the graph. Is any portion of it going to be an exact answer? If so, explain. So if we go back and look at our graph, we can see that our trapezoids have a lot of dead space. The pink trapezoid, not so bad. The red rectangle, dead on. That's going to be the exact amount for the red rectangle, assuming they don't go over budget, which they always go over budget. And then we have the green trapezoid here. That one has a lot of dead space. So we're saying that it's going to cost this amount, including this empty space here that's not part of the graph, is in the cost, but considering they usually go over budget, it's probably going to be pretty close or accurate, but the estimate itself is going to be an overestimate. So jumping back over here, and you can see I typed in that it is an overestimate because there is space in the trapezoids that is not part of the graph. I also added that the rectangle should be the exact cost because that was the answer to this part that wanted to know, is any portion going to be the exact answer? And then we get number 11, which says, if a portion of the graph between 500 feet and 1700 feet is approximated using 12 trapezoids instead of 2 trapezoids, would the answer be closer to the actual cost? And if so, justify your answer using the shape. So to answer that question, what I did is I took the part of the graph we're talking about, going from the 500. Actually, I did the wrong part. Let me fix that. No, I didn't. I picked the right part. And what we're going to do now is we're going to take and cut this into 12 trapezoids instead of 2 trapezoids. What is that going to look like? Well, sit back and hold on to your hats. I'm going to have a vertical line here and a vertical line there. So right there, that's going to be 1 trapezoid. Now I've got 2 trapezoids. If I was to take those 2, I could divide that into sections of 3, and I could divide these into sections of 3 right here. And then I'm going to take each one of those 3's and divide them in half. 1, 2, 3, 4, 5, and 6. So right now I have got 12 different lines, or 12 different sections that I've included there. If I was to take and go back and connect each of those sections, well, this is going to be a straight horizontal line, but watch what happens over here. This is actually going to be pretty dang cool. We're going to take and almost follow that graph exactly, going from piece to piece, meaning we are not going to have a gap above it. So right there, look at that. Isn't that beautiful? By cutting it up into smaller trapezoids, we were able to create almost a perfect covering of the graph, and that would end up giving us a closer approximation of what the actual cost would be. Now let's turn the page. For this one, they want us to use dimensional analysis to determine the unit of measure for the shaded area on each of these graphs. Now remember, we're going to be doing a length times a width kind of situation here, so I'm going to take and just set up a dimensional analysis chart here. We're going to do that, and we're going to do this right here, and I'm going to do this right here. And now I'm going to start plugging in my units. We're not caring about the actual values, we're caring about the units. So this is speed in miles per hour. So my miles go on top and my hours go on the bottom. And then this one is time in hours. So my hours go on top, and that means that when I take and divide out these 2 hours right here, what am I actually left with? Just miles. So my final unit is going to be miles. Notice it is not a unit squared, it's just miles. Now you take and pause the video and work the next 3 on your own. How'd that work out for you? For this one, I've got yards per hour, and I have time in hours. Once again, the hours divide out, giving me a final unit of yards. For this one, I have accidents per hour. Boy, that sounds scary if they're counting the number of accidents they have per hour times the number of hours. That is going to give you a total of a number of accidents you're going to have. And then for this last one here, we're going to have gallons per hour. Would be nice if they did something other than per hours here, just to mix it up a little bit. Once again, your hours divide out, and this one is going to leave us with gallons. Now we're on to the final page. The points in the table could be graphed on the coordinate plane and connected with a continuous curve. Label the axis, but do not graph any of the data. Sorry, announcements jumped in there. So it says do not graph any data in the tables. That's going to make it easy. Then determine the final unit of measures for the area. So right here we have miles per hour and time in hours. So I'm going to start off by setting up a dimensional analysis table. Whoop, that's not the one I wanted. I want a nice horizontal line right here. I said I want a nice horizontal line right here. And then we're going to take and stick in a couple of vertical lines just to make it nice and neat. And then I can start plugging in what I have. So they have time in hours, that's your top term, so that's going to be your x-axis, and speed in miles per hour, that's going to be your bottom item, so it's your y-axis. We're going to plug those in, so I have time in hours times speed in miles per hour, the hours divided out, leaving me a final unit of miles. Now for this one, time in hours, so that you can divide in here, time in hours, And this one is inches of rain per hour, so it's going to be inches per hour is how I'm going to write that. You go ahead and solve that one and the next one on your own. So finish 17 and do all of 18. So for this one, I have hours and then inches per hour. The hours divide out, leaving my final unit is going to be inches. For this one, I had a number of days on my x-axis. My y-axis is barrels per day. The days divide out, leaving your final unit for that graph is going to be barrels. Now, last two questions here. 19. What would be the unit of measure of the answer for the area calculation with dimensions whose units are raindrops per second and second? So what do we need to do? We need to take and set up another table. So we're going to take right here, and we're going to set up our vertical lines right here. And what are our units? Our first one is raindrops per second. So I'm going to say raindrops per means over, second, or means divided by, times seconds. Once again, your seconds are going to divide out, and what are you left with? Raindrops. And then finally, the final question says, if the final unit of measure of an area is feet, if one of the two dimensions has the units of feet per second, what's the other unit have to be? Well, that other unit has to be seconds right there. Otherwise, it will not be able to divide out and be able to get us feet. That is it. We have finished. That took a long, long time, but we are done. Make sure you get it turned in so I can give you credit for doing it. I'll see you in class.